Okay, hi. It's time for the lecture, and I got to go fast here. Remember what we did on Wednesday of last week? The little quiz we did in group as a group. You should have those notes out, and you should be looking them over, and you should be making sure they make sense because we're jumping off from there. We're going to do theorem. Let me get a different marker. Theorem 8, page 114. All right. This is a really cool, powerful theorem, and let me just state the way I want to state it. So let's let A be an n by n matrix, and I guess I'll go all the way across. Yeah, and let T sub A, taking Rn to Rn, be the linear mapping, be the linear transformation, the linear mapping, the linear function, whatever you want to call it. The linear mapping, the usual one, defined by multiplication by A. So in other words, I just mean, what does T do to a vector? How does it transform a vector x? You take A times x, all right? That's our setting. The theorem is T, F, A, E, which is something you should get familiar with if you study mathematics. This is a statement which says, I don't think I'm going to write it in. You can write it in. The following are equivalent. What it means is I'm going to write a whole bunch of statements down, and they are all logically equivalent to each other. And logical equivalence means if one of the statements is true, all the rest of them are true. If one of the statements is false, all the rest of them are false. So they are different ways to say the same mathematical fact, all right? So if it's true one way, it's true all these other ways. If it's false one way, it's false all these other ways as well. And what I want to do is your text lays them out, but I want to kind of have a little bit of fun, I guess, and draw kind of a goggle-eyed alien, which is the mnemonic for remembering this. So here's what we're going to do. We're going to draw, let's see if I hope I have room here. I'm going to draw kind of a funny pair of eyes. And what I'm going to put in the middle is the following. I'm going to have here the augmented matrix AI sub n. All right, so this is the matrix A, the n by n matrix here, and there's the n by n identity matrix. And I'm going to put a little squiggle here, and this squiggle, remember, means is row equivalent to. In other words, you can get from here to there, what I'm going to write here, using our standard row operations, or you can go backwards using standard row operations and get from here to there. And what I'm going to write over here, of course, I sub n, and then this will be inverse. So I'm talking about here doing the standard operations you would do to go from having A and I sub in here to, reduce A into the identity matrix, and the result will be when you do the row operations all the way across is you will take the identity matrix and turn it into A inverse. So let's assume that that's true, that we can do that, all right? That says a number of things. Well, one thing that it obviously says, so I'll make that be the hat, it says that A is invertible. Right, if you can read that. I mean, duh, that's what I'm really saying there, right? Well, something else that it's saying that's really obvious is A is row equivalent to the n by n identity matrix. And of course that's what I'm saying because from A I went to I sub n here, right? So let's see, what else? If that's true, then look, isn't I sub n the reduced row echelon form of A? I do row operations to get my diagonal of non-zero numbers. I turn them all into ones and take multiples going upwards to clear everything out. I'm going to get the identity matrix if I do that, if I can do that. So I'm saying that A is row equivalent to the identity matrix. This is the reduced row echelon form. So I can see right away there's a pivot in every row, a pivot in every column. So A has n pivots, right? A has n pivots. So stop and look at this. If I tell you A is invertible, I've immediately told you that A has n pivots. I've immediately told you that A is row equivalent to I sub n. If A is an n by a matrix and it doesn't have n pivots, then I'm telling you that this is false. It's not invertible. I'm telling you that this is false. It's not row equivalent to the identity matrix. So this thing up here would actually not happen, right? Okay, so we just got kind of started there. Let's see, what else can we do? I'm going to have, I guess, come off of here. I'm going to have some tentacles. So let me go like this, and let me go like that. All right, and what I want to say here is that if A has n pivots, I can solve any equation I want with multiplication by A for any vector. So that would say that T sub A, which takes Rn to Rn, has to be onto. Right? It has to be onto because A has a pivot in every row, so every possible equation I can form, every system, if I think of it as a system of equations, is consistent. So I can get any vector over here. I can get any vector. I can solve it for any one over here. So T sub A must be onto. And another way to say that really is to say that AX equal B has a solution for every B. That's really what I was just saying, wasn't I? No matter what B you pick over here, I want an AX to get to that B. I always have a solution. I always have an X, so it's onto. All right. Well, another thing then that is saying is that if T sub A is onto, or if A sub X equal B has a solution for every B, then that says I can always find a linear combination of the columns of A to give me any vector, right? Because remember, A times X is a linear combination of the columns of A, where X gives me the weights or the coefficients that I attach to the columns. So I can use linear combinations of the columns of A to get any vector over here in Rn, any vector B. So the other thing we'll just add off here, the little thing that comes off of this tentacle, is that the columns of A span Rn. Right? I can get any vector I want. Okay, let's come back over here and let's do a big tentacle off this way and something like that, all right? And I think what I want to say here is, I guess I'll put it kind of analogous. If T sub A is onto over here, I'm also saying that T sub A is 1 to 1, correct? Because isn't it true that A has a pivot in every column? So there are no free variables if I set up any kind of a system, which means there's only going to be one solution to any AX equal B I have. There will be a solution, but there will only be one, so I don't have multiple things going to this B, whatever it is. I don't have multiple X's, I just have one, so it's 1 to 1. And of course, that says then that if we just think of AX equals 0, this has only the trivial solution. Has only the trivial solution. Because you know that if this had the non-trivial solution, if there was some, set of vectors that got mapped to 0, then this wouldn't be true, right? Because if I can solve it for any one vector, I can solve AX equal B for any one vector, I can add on all the solutions to AX equals 0 to get a whole bunch more, and it wouldn't be 1 to 1, right? So again, you can see that those are equivalent. And we got another little thing coming off here, and that is that as over here, the columns of A span Rn. Here, since there's a pivot in every column, we know that the columns of A form a linearly independent set. All right, because there's a pivot in every column. Okay, what else? There's our kind of goggle-eyed alien with a hat and a chin and a beard and tentacles coming off the beard, and he's holding two bats. And there's a couple other things that we don't really even use that the theorem mentions. So let's put a left ear here that says A has a left inverse. And I think I've defined that. It's just a matrix such that if you multiply it by A on the left, you get the identity matrix, right? And over here we have another one that just says A has a right inverse. All right, those are all equivalent. So look, if I tell you, hey, I have this matrix A, n by n, and I happen to find some matrix B such that when I multiply them together, I get the identity matrix, you can immediately tell me that, well, the transformation T sub A must be 1 to 1. It must also be onto. A must be rule equivalent to the identity matrix. Columns of A must form a linearly independent set, right? Et cetera, et cetera. You can tell me all that because it's all equivalent to that. Suppose I tell you that I have this matrix A, different matrix A, n by n, and I can't find a C on the left. There's no C on the left. Not just that I can't find one, but there's no C on the left that when I multiply gives me the identity matrix. I immediately know the columns of A do not span R of n. The columns of A do not form a linearly independent set. I immediately know A is not row equivalent to I sub n, et cetera, right? So if anything here is true, all the rest is true. If anything here is false, all the rest is false, all right? So you can memorize the big list they give you on theorem 8, or you can learn to draw the cute monster. I want to do a couple of problems. Let's see. Page 117. So page 117. Let me do number, how are we doing on time? Okay. I just have to be somewhere real fast. I want to do number, I didn't mark it down. Oh, I'm going to do number 6, I think. Okay, what does it say? It says, unless otherwise specified, assume that all the matrices in these exercises are n by n. Well, yeah, this one is n by n. It's 3 by 3. Determine which are invertible. Use as few calculations as possible. Justify your answers. All right, so my matrix that I'm starting with is 1, -5, -4, 1, -5, -4. Is that still? Yeah, we're still on the screen. You can see it. 0, 3, 4, 0, 3, 4, and -3, 6, 0. -3, 6, 0. Okay, is this invertible or not? It's not asking me to find the inverse. It's just asking me to do, in as few steps as possible, determine whether this is invertible. Well, let me look back over here. Hey, A is invertible means that all this other stuff is true. A is not invertible means that all this other stuff is false. So why don't I pick the one that's going to get me there quicker? I think what I'm going to try to do is maybe look at the number of pivots I have, because I think that's something I can get real quick by doing some row operations here. So what am I going to do? I'm going to leave row 1 alone. I can even write it in here. 1, -5, -4. I'll leave row 2 alone because it has a 0 there. 0, 3, 4. And then I'll take 3 times row 1, add it to row 3. That's the new row 3. So 3 times 1 is 3. Add there is 0. 3 times -5 is -15. Add to there is -9. 3 times -4 is -12. Add to 0 is -12. Okay, now look, I'm not even going to write it out. I'm just going to say triple row 2 and add it down, and you get 0, 0, 0. All right, I immediately see not 3 pivots. I think there's going to be 2, but I don't care. I know so there's not 3 pivots, so everything over here, put a not in front of it, right? It's true if you negate everything here. T sub A is not onto. AX equal B does not have a solution for every B, et cetera, et cetera. In particular, A is not invertible. So that's my explanation. So A is not invertible, and it's by theorem 8. Right? It's by the fact that not 3 pivots means is not invertible if it's a 3 by 3 matrix. All right. Good. That was easy enough, wasn't it? Let me see, maybe one more. Okay, I'm just going to read this. Number 12. It's figure out what is it? Okay, each part of the exercise is an implication of the form if statement 1, then statement 2. Mark an implication as true if the truth of statement 2 always follows whenever statement 1 happens to be true. An implication is false if there is an instance in which statement 2 is false, but statement 1 is true. Justify each answer. This is basic logic. If P then Q is false, if you can find any kind of a situation in which P, the first part is true, but the second part is false. Otherwise, we say that it's true. I hope you have seen that before, but these should be easy, I think, in the context of what we just learned. So number 12, part A. If there is an n by n matrix D such that AD equals I, then there is also an n by n matrix C such that CA equals I. Okay, so if we assume that we have a matrix D such that AD equals I, we have a right inverse. The next statement is, then there is also an n by n matrix C such that CA equals I. Then we would have a left inverse, so that's true, right? By theorem 8, that's true. Okay, again, it says we're assuming that A is n by n, always. Part B, so that one's true. Part B, if the columns of A are linearly independent, hey, is that over here somewhere? The columns of A form a linearly independent set. If the columns of A are linearly independent, that you really say if they form a linearly independent set. But anyway, then the columns of A span Rn. This is true, and there it is. That's true too. So by theorem 8, that is a true statement. Part C, if the equation A equals B has at least one solution for each B in Rn, then the solution is unique for each B. Well, here I have that it has a solution for every B, right? I'm sorry, I read that. If the solution has at least one solution for each B, then the solution is unique. So here I have a solution, at least one, I certainly have one. And look, it's the same thing as saying that it's unique, which is, we don't actually have that statement said in those words, but it's the same thing as saying that AX equals 0 has only the trivial solution. It's the same thing as saying T sub A is 1 to 1. There is only one solution. So again, by theorem 8, that's true. This one is applying this one. This is a little bit different wording than saying that the solution is unique, but that's what this means, or I guess that's what that means, right? So again, that's true. Part D, if the linear transformation x to ax from Rn to Rn, if it is a linear transformation, if it maps Rn into Rn, pardon me, then A has n pivot positions. Well, if it maps onto Rn onto Rn, meaning it gets all of Rn, then I have n pivot positions. If it maps into, maybe not, because mapping into doesn't necessarily mean onto, right? So it could map into, and this could be false. If this is false, then that's false. So it is not automatically true that if x to ax, which is what t sub a is, t of x is ax, if that goes into Rn, it's not automatically true that A has n pivot positions, right? Because it could go into but not be onto, and if it's not onto, this would be false. So part D is false. It isn't always a true statement. Part E, if there is, I said D is false. Part E, if there is a B in Rn such that the equation Ax equal B is inconsistent, so this does not happen. This is false right here. Then the transformation x to ax is not 1 to 1. Well, look at that. This is not true. Therefore, this is not true. T sub a is 1 to 1. So that is, in fact, a true statement. If this is false, then that is false. That's what it's saying. So think of that very carefully. You've got to unpack that a little bit. All right. If there is a B in Rn such that Ax equal B is inconsistent, meaning this is false, then this has to be false, and that's what that's saying. Then X going to Ax is not 1 to 1. And so, in fact, that part E is true because when that's false, that's always false. Okay, great. Let's see. I think that's maybe about where we are. Look at number 16, then I'll stop. Is it possible for a 5 by 5 matrix, so that's going to take R5 to R5, the multiplication by A will take R5 to R5. Is it possible for a matrix to be invertible when its columns do not span R5? Why or why not? Well, if it is false that the columns of A span R5, then it is false that A is invertible. So by theorem 8, the answer is no, it can't be invertible if the columns don't span R5. Okay, so you can see this is a very powerful theorem, and really it all comes down to doing row operations, right? Everything on here you can interpret in terms of row operations, and really it's all tied together by looking at the goggle eyes here, right? This is kind of the key right here. If this is true, everything else kind of flows from it. If this is false, the negations of everything kind of flow from it. We shall stop here. We shall stop here. Let me give you some homework. Page 1 through 17, page 117, 1 through 23 odd. Okay. Have a good rest of your break, and I'll see you on Monday.